So the first thing Ray did when he found something was to take it apart and put it back together. And I spent 40 years watching Ray take things apart and put them back together. And it was a great 40 years. We had a wonderful journey together. And I must say, I spent the last 4 days watching you guys take theories apart and put them together too. And I'm very honored that you're doing this kind of work. And I'm very honored that some of you are using some of his ideas in your toolkit to work with. So I'm not going to be speaking as a mathematician, but Ray shared his thoughts with me, and I thought it would be fun to share some of those thoughts with you so you could see a little bit of how I saw Ray think about things. Now, Ray's main goal in life was machine learning, and that meant prediction, but not just prediction, but how good the prediction is. So specifically, I'll talk a little about Ray's theory of inductive inference as it uses computer programs considered like theories. And then I'll talk a little bit about how to look for better theories, mainly with a method Ray called Levin Search, after Levin, who defined it rigorously. So to begin, here's a picture of Ray taking apart a scooter we found in the trash. He took many notes about them, so that was like a program telling how to make the scooter. Let's see, Ray built a house from descriptions in a book that were, it's sort of like a recipe, which is another version of a program. This is his lab in high school. Ray is a guy over there on the right, and I don't know what they made in those labs, and a lot of those things didn't work, but they made them. Now the scooter has a sequence of physical operations that can be used to describe or make it. And operational definitions are a program, like a computer program. And one of the things that Ray showed me was that if you can't make an operational definition of something, very likely you don't understand it. And it's true for us writers, it's true all over, in all kinds of fields. So I'm going to show you first the special abstract computer for the computer programs, which you all know about. This is your Turing machine. And the important thing is over here is the output. And it has a one-way input tape, one-way output tape, a bi-directional work tape that goes off into infinity. And it's a little bit like a container. This Turing machine will have some kind of instruction set to run it. In our real world, that would be something like C++ or Python or something, and other instruction sets. So that's that part that goes in. And then you have any extra information that you're going to add in our real world. So that goes in. And then you have the input program. After all, everything's in there and it's chugging along. You have the input program that's going to produce the output program. At least that is sort of how I understood him to say it. So one Turing machine can perform the activity of another one because of you can have a translation thing. So I'm going to talk about Ray's theory of inductive inference. And I'm going to do in a single page, I'm going to do the entire theory of inductive inference the way Ray showed me. And it's going to be kind of like a tour guide, as if we're going through the Panama Canal or something. So here's the entire theory of inductive inference in one page. And there are three parts to it. This is your Turing machine. This is algorithmic probability. And this is phase theorem. And we're going to go into the Miraflores locks. This will be the Miraflores. This will be the Gatun Lake in the middle. And this will be the Pacific gates going out. And we're going to go in. This is our programmer here. He programs like this, flips a coin. And that's one of the important things, the input program. And the other important thing is the output, which is going to be a problem sequence. It's going to be like question-answer pairs, or it's going to be like Ben Goertzel's children's IQ test, and you're going to try to find out what comes next. So this guy is he's a very important programmer. He's very, very powerful, actually. And the important thing is he's very, very honest, and he's very, very stupid. So he does your input program, which is a random string, and this is the Turing machine M, which is your system. And the beginning ones, the first program, of course, fails, goes through and operates and comes out a bunch of nonsense. The second is nonsense, third is nonsense. But eventually, S1 actually produces the output. And the thing is that you can actually measure how the rank of the program this way, so that you can actually measure that the shortest programs are producing the output. And an interesting thing is that Ray developed this in 1960, he was publishing it, and it's a little different from the complexity that is known as Kolmogorov complexity, because Kolmogorov and well, Ray did it first in 60, and he used program length complexity to gauge how long the size of the complexity of the output series. But Kolmogorov and Chaitin use today's output. So they would do 1, 1, 1, 1, 1 for today. And Ray wanted to do a longer string into the future, so that he would have the 1, 1, 1, 1, 1, and then in the future, the 1, 1, 1, 1, 1. So his complexity is a little bit different from the Chaitin type and the Kolmogorov type, because it goes into the future. So anyway, you have this guy doing these programs, and one of this goes through, so that gets to be added. And here's your S1 being function with X, the result, so that gets to go in here, and this is the length. This is like, as you do the flipping, 50%, 25%, so there's your probability there, and more go through, and they fail, and another one goes through, and it gets added, and another one goes through, and it gets added, and eventually they all get added, so that you get a universal distribution of the probability of X with respect to this guy is the sum of all the programs that you are able to produce. And in an abstract computer, that goes on forever. And then I'm just going to do a binary string so that it has a 0 or a 1 coming out. But you can do it all different ways. You don't have to do a binary string. You can do bags. You can do sets. You can do all kinds of things as long as you are aware of the measure, which is a probabilistic measure. So anyway, this will be the probability of the whole thing. And you take you take the probabilities of the ones that went to 0, and that you can put that here because you have the probability of X. And you can put, this is the probabilities of the guys that went to 0, the probabilities of the guys that went to 1, and you have a ratio of X1 over these. So you go out the Pacific gates with a probability ratio of the guys that went out. So that's sort of what he showed me about how you do that. With Bayes' rule, it's often used, but it's usually used like frequency. So you have like a Greek urn filled with events that are hypotheses, whereas Ray has a Turing urn, which is filled with explanations. It has explanations of everything in the universe. It's like it has an opinion about everything. The less probable is more random. He came to the definition of randomness, but via probability. And he thought actually that might, yes?
5 minutes.
Huh?
5 minutes.
5 minutes left? Oops. Okay, well, then we're going to have to go through everything very fast. Probability wasn't accepted. This is the guys, Ray talking to Marvin and Ed Fredkin. People didn't like probability. Now they do more. This is also he got a lot of inspiration from science fiction, and that's back in the 50s. Okay, so I'll go to multiple theories right away. the second thing that Ray did was to use things in a way that wasn't intended. So here's assaulted in a turban. Here's Ray's Halloween costume, Ray in a turban, and the original owner of the turban is this guy. And what he's done is he made a different description of it. And I'm going to do one more quick one, because this is a description of things in the present day. So he also did descriptions of things in the future. We lived in the flower children age. This is a picture of our flower children, love in the park type things, which really was mostly guitar playing and stuff like that. This is actually later, but this kind of stuff we wore. This is actually quite a bit later, but it shows the costumes. This is, in those days, you protested the Vietnam War, but this is a protest later against Lotus, which tried to patent a keyboard layout, if you can believe it. That really shouldn't do things like that. So here is the second, wait a minute. This is the next description. This is a description of Ray's electric pot smoking machine. Then this is what Allen Ginsberg actually breathed through that tube. And it collects the smoke really well, and you breathe through it. So I'm going to show you this as a multiple description. Here is a coffee immersion, hot water immersion heater. You put that in boiling water, this little coil goes in boiling water, you stick that in there, and your water boils, and you get your coffee. So now, meanwhile, back at the hookah, here is the bowl of the pipe, and as we take that out, and we see the immersion heater, but he has looked into the future, and he's decided this could be used with like a different description. It combines a description of a pipe and a heater and different things, and it was a future-oriented thing. So, and it was fun to, yes.
Did it burn the pot or just heat it? Because if it
No.
just heated it, it would be a vapor.
Yes, that was the, I'm sorry I didn't make that clear. It was, the idea is to have a heat regulator. He has it, actually it's attached to a transformer here, which regulates the heat so you get a very smooth smoke. And it isn't like pulling a joint when you go, so that's an example of the description, and I only have a couple more minutes, so I don't know how we can do this. So this is Lsearch. I'll just say really quickly. You're using Lsearch as an action you have a trial program, and you test them in order of increasing time over probability, where probability is the probability of success of the ith trial, and TI is the time needed to generate and verify that the trial is correct. So it's another complete system since it includes any input program and thus any output. It means no program is outside the search space, and one of the problems with most search things is that they don't acknowledge the outside the search space. Conceptual jump size is a measure, and Lsearch is an action. Conceptual jump size is the measure of the computational cost needed to solve a problem. It is the time divided by the probability of a successful algorithm describing the sequence of observations. And so this will be the probability, and this is the time for that particular one. And the probability because of the relationship between the time and the probability, you can do probability cost. So you could actually have a little bit longer string if it's faster. And by the way, here are the observations down here. I'm using the tread. He would sort of picture things for me so that I could see them. And this is the kind of way he showed me things, so that even though I don't have the mathematics, I could have some idea of what was happening. So I'm using the concept as a tread. I'm using conceptual jump size as the riser to a stair, and Lsearch as the action of going up the stairs. And actually you would have millions and billions of these guys all going up the stairs, swapping concepts, and so this isn't quite as good as a concept net, which is more what Ray might have done. But anyway, we only have a couple more minutes. One problem with the conceptual jump size is your sterilizer can be very, very high. But I do want to say this quickly about observations, that if you are able to go up the stairs, you're able to see, first the stuff might look like the town dump, but as you go up higher, you're able to see more and more structure, and it means you're able to predict more into the future. The point is, the more structure you can see, the more you can see into the future. And not only can you predict the future, Ray often said it's as hard to predict the past as the future. So you may be able to use past data and be predicting back that way too. So anyway, that's his sort of a picture that I got from him about these things. We've been working on a website, and we're scanning some of his notes. This is the first scan that got up there. This, if you want to know a little more about Lsearch, this is his ideas of Lsearch in 1979, when he was talking a lot about computational cost and how to limit things. Let's see. I guess I don't really have time for much more except to say that Ray did think of many ways of trying to shorten that problem with the high conceptual jump size. How are we doing? A couple more minutes?
Well, it's minus what you can.
Okay, it'll be just 2 more seconds. One of the important things is that he had the idea of resource-limited prediction, which dealt with 4 basic factors: the prediction itself, the reliability of the prediction, the sample size, and the computation cost. And those are the main things that you have to think about when you're trying to work on a new system to control that big mess. A quick idea I'll just mention, that Alex Solomonoff, who's one of the clan, is very interested in this field too, and he suggested, which probably you guys have probably suggested too, that if you have the running code that has actually printed out some of the X correctly, some of the observations correctly, you can give it more time that way. The idea is how much time to give the search and the different ways you can reduce the time. Also with agents, I just want to say one thing about agents. Marcus Hoover, Orso, and Tor Lattimore have been working a lot on agents. The idea is to do a Bayesian type of agent. Their definition of an agent is one in the scientific world who can make experiments to get more meaningful observations faster than waiting for the universe to provide them. And a question or two I was thinking about with that is where you might start it. Maybe, do you know where you're starting? Because sometimes if you're doing some types of problems, you start with the beginning of the problem set. But if you're doing observations, you might want to think about where you're going to start in this sequence. And with noise, they rule out noise. They are able to distinguish data from noise. But one thing Ray thought about noise is that today's noise may be tomorrow's data. So maybe you can save a little of the noise, and if you have problems, you go back and you look at the noise. And Ray's system makes it more easy to go back and forth between these different concepts. And the other thing that I was thinking about with an agent might actually introduce noise. So I don't know whether people are actually looking carefully at the kind of noise an agent might introduce. Won't have time to do the Ray in outer space, but at the end of my report I have a little bit of science fiction, because in honor of Ray liking science fiction. So I have his computer there in outer space. This is the computer that Ray made back in the 70s, and he spent days and days wiring it. And after I don't know, weeks of doing this, and he was able to stick to one thing for a long, long time. I get so bored, but it was okay. And at the end, there was this little red light, and the little red light turned on, and the little red light turned off. And so I'm going to turn off now. And I've enjoyed talking to you very much. And so that's a little bit about how I think Ray thought. So, thank you.